Hello and welcome back to the MCAT grind. Okay, it's on. Alright, so physics chapter 3 is thermodynamics. These are questions you will see on basic calculations asking you to determine how much joules or energy is lost in this process. For example, you were given a tungsten cube and you were to melt it down fully, how much energy would that cost? And so forth. So it's good to know a few equations. Thermal expansion states that if you heat up an object enough, it's going to expand. And lengthwise, it will be expanding by this. The changing length will be the specific constant for length expansion multiplied by the original length times the change in temperature. Note that because it's changing temperature, it doesn't matter if it's in Kelvin, if it's in Fahrenheit, Celsius, doesn't matter. It's just in changing temperature. Actually, no, it can't be Fahrenheit. Sorry, Celsius or Kelvins. And volume will be the same. The specific constant for volumetric expansion multiplied by the original volume times the change in temperature gives you the expansion amount. Alright, then according to the 0th law of thermodynamics, heat transfer occurs when you have a hotter object and a colder object. They will eventually dissipate heat so that they're the equal heat. And then if a third object comes into play, and the second one and the third one is in thermal equilibrium, the first one and the second one are in equilibrium, the first and the third one will also be in equilibrium. So basically, there's a diffusion of heat from one to another. And there are three ways this occurs. First one is by conduction, where two objects are in direct contact with each other. By convection, where through air or fluid, or air technically is a fluid, by which heat travels through, or through water, any other medium, fluid medium, they're not in direct contact. Or by radiation, so that's electromagnetic waves, so for instance from the sun heating up things, or by magnetic spins and radii of heat. Those are also ways of heat transfer. To calculate and measure specific heat, the amount of joules and energy it will give off, you need to use the mass of the object and the specific heat in which it's going to either gain or lose energy, and amount of heat it takes to raise its temperature, and as well as the change in temperature. This is the exact amount of joules that the object will change by. So if you add change in temperature, you will require this much energy. So you can know the specific heat of water is 1 cal per kg. So to increase the heat of 1 kilogram of water, you need, by 1 degrees, you need like this specific heat, which is 1 cal. Okay, so you can just use 1 for water, but rest will be given on the question itself. So for that specific mass, you need a specific heat and the constant, and once you have a change in temperature in mind, you'll require that much energy in joules. In joules or cal. I think 1 cal, 1 small c Al, 1 cal equals to 4.18 joules. I think there might be more afterwards, but just remember around 4.18. And not to be confused with the big cal, with the big C, because that's 1,000 small cal. So that's kcal. That's basically the food calorie. Big C, Al. All right. We also have energy requirement for melting or phase change. If you ever have melted an ice cube, you will see that before raising up the degree temperature, you will need to stick to that temperature before it actually melts and changes to water. That's the heat requirement for fusion, which is melting. And also the heat required for vaporization, which is turning from water into steam. The phase change also require energy itself. Think about like evolution requirements. So that is to be added to the Q requirement for the changing in the temperature within the same state. The changing state will also need a energy addition. Work is P pressure times V volume, and it is calculated from the gas perspective. So from a gas, if it exerts out work, that means it's increasing in volume by itself while maintaining the same pressure. So that is work done by the gas. Now we have certain processes to know. Work and heat are processes functions, which means that the way, the path they go through matters. This is different from state functions, which is position, density, volume, mass, which are set and doesn't matter where it begins and where it ends. Heat and work, it depends on the path they go through. So from two given points, if that work needs to take a lot more path around, that takes a lot more work. Think about if you were pushing a block, right? For displacement, it doesn't matter. As long as you end and begin in the same point, you have done no distance. Your net displacement is 0. However, if you're calculating from distance, then if you started from one place and you walked all the way around and come back to the same place, you had moved about a certain distance, and of course that took work, right? Because of friction and all of the movement around. So that's distance is processes function. Now, in regards to work, we have isobaric, isothermal, adiabatic, and isochoric processes. Isobaric means that we have the same pressure throughout that process. So if we start at point A and to the second point, there has no pressure change. It remains at the same level. For isothermal, there is no temperature change. So the overall temperature has not been increased or decreased. Adiabatic means that there has been no heat added into the system, and isochoric means the volume has stayed constant throughout the process. Now, this brings us to the first law of thermodynamics, which states that the temperature change, U, or the total energy gained, is equal to the heat added minus the work outputted by the gas. This makes sense because when you add heat to it, it should warm up, right? And if the gas itself decides to do work and work out and use that energy for something, then we have to take away from the heat we added in. Think about your investments versus like the spendings. Investing in versus the spending out from that account gives you the total amount you have left in that account. So we have isobaric, which states that same pressure throughout the process. So we modify this equation to be still the same because same pressure doesn't affect our work equals pressure times volume. Isothermal process, however, the same temperature is overall a result from Q minus W. So the overall energy gain is 0, but that could mean that Q and W equal the same. Perhaps there's no heat added and nothing has been done, right? But it could also mean that if you added like 100 joules of energy and the gas also used up 100 joules of energy, then they are basically the same as each other, right? Maybe you got $100 as a gift, but you spent all that $100, so your net amount of money is 0. Adiabatic means that no heat is added, so Q equals 0. So what that means is the overall temperature gain will just be whatever the work has been done by the gas. Perhaps the gas is doing some work expanding, then that will mean that the overall temperature change will go down because it's negative. Isochoric means the same volume throughout. So if it remains at the same volume, there has been no work done, right? By P times V. Sorry, I did not add P times changing V. Right. The pressure doesn't matter too much, but if the changing volume is 0, then there's no work done by the gas. Okay? P changing V. So if changing volume is 0, then there's been 0 work. So that just means the overall temperature will just be determined by the heat added. Alright, and we have the second law of thermodynamics, which means entropy which like the account of randomness is determined by the reversible heat added divided by the temperature in Kelvin. This states that anything in the universe will always get more random and disordered. However, you could make a system more ordered at the expense of the surroundings being more disordered. For example, if you want to stack a block of bricks up, you'll have to expend that energy and move the particles around your hand in order to stack those particular particles. So you can make local organization, but the overall disorder of the universe will always be more than 0 and go up. Alright, that's thermodynamics. Take care.